Hi, my name is Sweeta, and this is Lab 1 Charged Tapes. The purpose of this lab was to investigate electric charge using simple materials. We observed electrostatic interactions between pieces of clear tape, and used those interactions to estimate the amount of excess charge on the piece. To do this, we used two computational models, one that treated the tape as a point charge, and one that treated the tape as a line of distributed charges. The materials we used were clear tape, a ruler for measuring distance, a charged plastic object, like a pen, and glow script. The final estimated charge was about 8.94 nanocoulombs. Electric charge is a fundamental property of matter, and it comes in two types, positive and negative. It is measured in coulombs, and its smallest possible charge is the elementary charge, which is 1.6 times 10 to the negative 19 coulombs. We use Coulomb's law to model the electric force between the tapes. The equation is F equals K Q1 Q2 over R squared. This law tells us that the force between two charges is proportional to the product of their charges, and inversely proportional to the square of the distance between them. In our case, when the upward electric force balances the downward gravitational force on the floating tape, we have F electric equals F gravity equals mass times gravitational acceleration. For the results of the U-tape, at first here I wanted to see if the tapes were negatively or positively charged. I had my base tape down on a flat surface and adhered another piece of tape on top. With a swift pull on the top tape, it would now be charged. To specifically find out whether it was positive or negatively charged, however, I had to grab a plastic pen and negatively charge it by rubbing some cloth on it. And from then, if they both attracted, then that deems the tape as positive. So we know that opposite charges will attract. To test if like charges will repel, for this part we needed to float one piece of tape above another. Tape B would be our system, while tape A was the surrounding, which acted on the system. Tape B was then able to repel away from tape A, specifically 0.019 meters away. From our data, we wanted to find the number of electrons that were lost. We knew that the mass of the tape was 0.0002 kilograms. We could use the mass of the tape and gravitational acceleration to find the magnitude of gravitational force on the tape. To find electric force from there, we'd know that because tape B was floating and still, which would make net force 0, electric force should be equal to gravitational force, so they're the same number. From then, to find the electric charge, we would just use the electric force equation, which would be Coulomb's law. Finally, to find the number of electrons lost, we would take the charge of the tape divided by the absolute value of a charge of an electron, which would give us 5.59 times 10 to the 10th power. On my data, we also have the number of atoms on the tape surface, which was 3.86 times 10 to the 17th. For the fraction, we can get the number of electrons lost divided by the atoms on the tape surface, which would come out to be 1.45 times 10 to the negative 7th power. This means that out of all of the atoms on the sticky tape, only 1 in every 7 atoms gave up an electron. This is the code used to process the data I measured, assuming that each piece of tape acts as a point charge. As you can see on the right, the levitating piece of tape is in equilibrium as the downwards gravity force is equal to the upwards electric force. The magnitude of the electric charge was found using the calculated gravitational force and measured separation distance. Using these assumptions, we see that an electric field of 2.23 times 10 to the 5th was created at the location of the levitating piece of tape. Here are some assumptions and errors. Tapes have equal charge, charges either lumped at the center or distributed uniformly, or charges do not leak off the tape during observation. Our errors included measuring tape float distance, uneven charge distribution, and environmental factors. Finally, what if protons were negative and electrons were positive? Basically, nothing would happen. The labels would change, but not the physical behavior. The two computational values for Q are different. Why? The point charge model assumes all charge is concentrated on the tape center, while the line charge model distributes the charge along the tape, accounting for extended geometry.